Okay, welcome back to my Project Euler series in Python. We're on problem 3. So, largest prime factor, problem 3. The prime factors of 13,195 are 5, 7, 13, and 29. What is the largest prime factor of the number 600,851,475,143? Okay, so obviously, let's break this problem down. So, numbers are either primes or products of primes. So if a number has factors that aren't prime, then even those factors are products of primes. So everything can be always diluted down to just products of primes. And these are called prime factors. So I'm guessing we're going to need some code to work out these prime factors. So how to do that? Well, we can sort of take inspiration from a concept called the sieve of Eratosthenes, or Eratosthenes, I've heard it pronounced. Basically some Greek guy that was saying we need to keep going. We need to take like a grid of numbers, for example. Let's try and do it here. So let's just do the numbers 1 to 10. Let's see if this visual will work. Okay, we kind of need to start at 2 for this. So if we take 2, then we can rule out all of the multiples of 2. So just count 2 each time. So 4 is not going to be prime, 6 isn't going to be prime, 8 is not going to be prime, 10 is not going to be prime. Then we move to the next non-crossed out number. So 3 is prime. So now we just take all the multiples of 3. So 6 isn't going to be prime, 9 isn't going to be prime. Then we move to the next non-crossed out number, 5. So 5 is prime, and then we take out all the multiples of 5, etc., etc. So yeah, that is sort of how the sieve of Eratosthenes works. So we can do a similar thing to find the prime factors, is we can keep diluting down a number until we are left with its factors. So let's see what we can do here. So let's take n equals 13,195. See if we can recreate the example. So if we start with 2, for I in range 2, let's just put the upper bound on n for now. And then we want to chip away at that. We want to keep dividing if it's divisible by the number. So, for example, the first one's going to be 2. So if n is divisible by 2, then we want to store the 2 somewhere as a factor and then divide n by the factor to reduce it to the components of the remaining primes that are the factors still left in the number. And then we can keep iterating through and keep churning those out. So if n is divisible by I, then we want to say print I, and then we want to do n integer division equals I, which basically means it's going to reduce n, it's going to divide n by I. So if we keep doing that, it should print all the prime factors, because it's just going to keep, so say if 4 was a factor of the number, so say it's 28 for example, then if 4 was a factor, then, okay, I have done this wrong. So if we do a while here, while, it's not an if, it's a while. So whilst n is divisible by I, keep dividing n by I until it's no longer divisible, and then you can iterate. So for example, 28 prime factors are 2, 2, and 7. And what that means is we'll start with 2 and we'll go through while 28 is divisible by 2, which it is, so we'll print 2, and n will then be replaced by 14 because we'll do the integer division from 28 with 2, and that will leave us 14. Then we'll go back while 14 is divisible by 2. Well, that is the case, yeah. So we'll print 2 again. And then we'll be left with 7. So 7 is not divisible by 2 anymore. So it's going to pop out, going to increment I to 3, and then that's not the case, so it's going to keep going. 4, well, 4 is not a prime, but it's still going to hit 4 in the list from 2 to n. But we know already that 4 is not prime, but it was divisible originally. But because we've already taken out the 2 2's that make up 4, it's not actually considered a prime factor because it's not prime. So that's how the sieve of Eratosthenes comes in, is it won't give you 4 as a whole factor. It's already given it broken down here. So hopefully that made sense. And this should give me 2, 2, and 7. Nice. Okay, so now let's do, I think it's 13,195. 5, 7, 13, 29. Okay. That's perfect. Okay, so let's do this number. Hopefully it's just a matter of pasting it in, 600 billion and all the rest of it. Okay, sweet. So it's come out with these numbers, but it's just not finishing because it's got to count all the way up to 600 billion. So we might be waiting a while. Let's see. So maybe we only have to go up to the square root, because this is the thing with finding the prime factors of a number, is if you only go up to the square root, even if it's prime, for example, 25 is 5 squared and 5's prime. So if you go up to the int value of the square root of n, then just grab the math function, then, so if we're using 25 as our example, then if we go up to 5, then we know that if there's a prime factor bigger than 5, that it will just be what is left as n at the end of it. So let's think of a number where this is the case. 21. If we do 21, then if we go up to the square root of 21, which is somewhere in between 4 and 5, then we would have only gotten up to 3, and therefore 7 wouldn't have been found, because we know that the prime factorization of 21 is 3 and 7. So if I do this, it should only give us 3. Right, but obviously we know that it's 3 and 7, which means n is the remaining prime factor, because we'll only get as far as the square root. But if the square root is one of the factors, then it should get there. So if the remaining factor is above the square root, then it should be in the n variable. So if we say if n is greater than 1 by the time we get here, then that means we haven't fully divided through the number, and n is holding the place of the remaining prime factor, so we can print n as well. So now this 21 example should work. Nice. And if we go back to the original number, then that should also work the same straight out the box, and we should be all good. Okay, let's just double check with 25 to see if it works with the square root. Okay. So that basically means we didn't reduce n. I guess, because the range function is actually non-inclusive, so we need to do +1 so that we can actually include the square root, because what's happening here is the square root of 25 is 5, convert that to an integer is 5, so it's going up to but not including 5, so we need to do a +1 to actually include the value. So this should work, yeah, as the 2 5's. Nice. Okay, let's leave it there. So what we actually want is the largest prime factor of this. So currently it just gives us a list of prime factors. Well, not even that, it just prints them out. So what if we stored them as we went in a list? Let's call it a list of factors. and then factors dot append I, and this will need to be n now because n is the remaining factor. Okay, so let's see if we can print factors. What should this give us? Okay, sweet. So in an ideal world, the program will just print the answer and only the answer. I like to be a little bit pedantic like that. So let's think, it wants the maximum. Well, if we're counting up to the point where I is the factor and it's always increasing, then it should be the last thing added to the factors list. And similarly, if n is a remainder, if n is holding the value of a prime factor that's remaining, then that means it was less than the square root, which means it's also going to be the biggest thing once we append it. So this tells us that the last thing in the list is always the biggest. So we can just grab the last thing by using the -1 placeholder. And there we go. Okay, I'm pretty happy with that. Let's see if that was correct. So was it 6,857, 6,857, nice. Okay, so yeah, that's problem 3. I will see you on problem 4.